Hi guys, I'm Ethan,
I'm Owen. I'm Sylvan.
and we implemented MLKit, a learning library with Rust. And just to give a quick introduction, we wanted to use some more low-level applications of Rust from inspiration from very famous Python libraries like PyTorch and TensorFlow. Um, just given that, ML algorithms are a bit of a misnomer and like there's a lack of representation in the Rust space. And so we wanted to empower the aforementioned applications to develop this library. And so I just want to go over the kind of initial plan that we had and talk about some of the developments and changes. So originally we wanted to work on some minimization techniques like Newton's method and gradient descent, and some more basic classification algorithms like perceptron, SVMs, and K-clustering algorithms like k-nearest neighbors, etc. And eventually that would lead to more sophisticated algorithms like neural networks and convolutional and recurrent neural networks, etc., etc. And um, right from the onset, we kind of shifted more so towards gradient descent and neural network implementations just because it was a collective decision and we believe that it'd need more time. And so we can kind of go over like the major implementations of our library. So we heavily utilize Sylvan's Matrix Kit, which is a linear algebra library implemented in Rust. And then we also implemented singular value decomposition, which can be used for image compression and different applications that will be explained later. And we implemented stochastic gradient descent, which is kind of our training engine for both our neural net and convolutional neural network. And of course, our neural network, which is our fully connected network with activation functions and different loss functions and gradient updates. And then in addition to that, we just kind of added convolutional layers and pooling layers to create our convolutional neural net. Thank you.
Yeah, so for evaluations, I'll first talk about our neural networks. So this is a look at our fully connected neural net. Here's just kind of the structure of the neural net. It's basically all you do to specify it is just give it some weights and biases, and then a list of activation functions. You can also just specify the shape of the layers. Like I want this layer to have 700 layers, this one to have 16, 16, and then our under the hood we can compute kind of randomized initialization weights and biases and stuff like that. For activation functions, we have this kind of like wrapper enumeration type called AFI, which lets you specify which type of activation function you want. So you could use ReLU or sigmoid or the sign activation function. So there's a lot of different ones, and each one it will compute all the gradients accordingly, basically under the hood. And of course, so this specifies your list of layers, basically, just you can specify the shapes or the actual weights and biases, and then that kind of specifies a neural net. And then we have all these functions on that neural net which can do any function the user might want to use. Like for example, it can compute all the gradients. It can just classify a single input. So you can give it an input, it'll forward pass through all the layers, and then give you the output that you'd get, and then give the classification it would choose based on that. In addition to the neural net like class, we also have a SGD trainer class, which basically handles all SGD training. So that like kind of computes all these it segments a training data set into a bunch of different mini batches, randomly sampled, and then kind of runs SGD, runs the gradient updates on a neural net, all under the hood. So yeah, and now Sylvan will show a quick demo about how to actually use this neural net, use our library.
Yeah, so actually this demo is pre-recorded, so check this out. Hey, so I'm going to show you what it looks like to create a project using our machine learning library and use it to train a neural network to recognize handwritten digits. So first we'll go ahead and create a new Rust project, we'll call it AI demo, and add the MLKit and MatrixKit dependencies. After we've done that, inside of our Rust project in our main function, we'll go ahead and first load in the two training data sets. So this is the 60,000 image data set of the training images, and then we also have the testing set, which is 10,000 images. So we are going to let the trainer be the SGD for stochastic gradient descent trainer, and it'll be using these data sets with a squared loss function. Our library lets you do any loss function, well, pre-coded loss functions, but we're going to be using squared loss for now because it makes the most sense, I think. And we'll go ahead and start with a random neural network. This basically initializes all the weights and biases to be random, sampled from a truncated normal distribution. So the images are 28 by 28 pixels. So the input layer is going to be 784 neurons. We'll have 4 layers total. So the input layer and then 2 hidden layers. They'll each have 16 neurons each. And then the last one, because we're outputting a guess as to a digit, there's 10 digits. So the output layer is 10 neurons. Since we have 3 non-input layers, we'll also have to have 3 activation functions as well. So these activation functions will just be using the sigmoid function, which maps values, any real value to a number between 0 and 1. And for our gradient update schedule, so this is how the gradient changes from batch to batch after we've computed the gradient. Usually this is done using a fixed learning rate, so taking the gradient, scaling it by our learning rate, and adding that to our parameters. That's what we'll do for now. We also support other methods, so this could be adaptive, for example. We could use Adagrad, which is in our library, or we could do, other things. We'll train on 100 epochs, and first, using trainer.cost, we can just get the original cost of the random network, so we know what our baseline is, and hope we improve from that. Then we can go ahead and train on this neural network using a gradient update schedule, using our 100 epochs, and having a batch size of 32. I'm going to set verbose to true, which is going to have our network print out when it's training each epoch, just so we can keep track of how the training is going. Okay, next we'll go ahead and measure the final cost after the training is done. And then this trainer.displayBehavior method just lets us view how well our network did at the end. It prints out the final cost, the final accuracy as a percentage, and it shows a random subset of, here we're going to do 10 data samples. So it'll show us 10 digits that the MNIST library has, and it'll show us how our network performed on them. And we'll just go ahead and run that. So I'm speeding up the actual time it took to run this process. In reality, it took about 6 minutes, but that's kind of long to put in a video, so I'm speeding it up. Okay, we're finished now. So let's look at the results. Here we've printed out different images that our dataset has. We'll see the original cost of the network, or the final cost was about this low number. So we can see, oh look, there's a 4, and our network recognized that as a 4 with this little number next to the 4 that I've highlighted. Is it sort of the network's confidence that it's a 4? That's the actual value that was assigned to that neuron corresponding to 4 in the output layer. So it's pretty sure this is a 4. And here we are recognizing 1s, 6s, 8s, and so on. Yeah, so this is how to use our neural network library to train a neural network. That's it. And you can see the final accuracy is 93%.
Okay, so yeah, thanks Sylvan for that demo. Now I'll talk a bit more. I'll talk a bit about our convolutional neural network implementation. So just a quick explanation. So a convolutional neural network, or CNN, involves is based on taking advantage of the spatial structure of an image, for example. So for example, a fully connected layer needs to have an input for each individual pixel of an image, whereas with CNN, you kind of take advantage that it's a spatial structure where at each space and time, it might have a certain feature that you want to identify, like a straight or curved edge at each point. So the convolutional layer basically works by passing a filter across the image, and then kind of each filter has its own weights and biases that are then shared across all of the input pixels of the image. And so then that really reduces the number of parameters you need to specify the model. So yeah, you pass this filter along the image, kind of convening the convolution of the input image with each of those filters, and that gives you this kind of inner hidden layer of different intermediate smaller images, which kind of identify the features of the image. So another common type of layer in a convolutional neural network is a pooling layer, which basically just reduces the dimensionality of the images. It passes a window across the image, and each window it computes, like, for example, the maximum, the average, or the sum, and so that basically combines all of the elements in one window into one element of the output layer. So you can see it reduces from these large images to smaller images. So usually a CNN involves a sequence of these convolution, then pooling layers to kind of extract the features of the image. And then finally, there's kind of this smaller, fully connected network that actually uses those features, those identified features, to classify what the image is. So the idea is this should require way less parameters than a fully connected network, because there's all in the convolution layers, all of the parameters are shared. So yeah, this is the background of a CNN. Our implementation, there we go. So just to give you an example of uses of how a user might use our CNN library is basically you can define a whole convolutional neural network in just kind of one line like this. You basically just pass it a list of the different layers. So for example, here I'm defining a convolutional layer, here I'm defining a pooling layer, then a differently sized convolutional layer, etc. And then these are two full layers at the end. For the pooling layer, you can specify, do I want a maximum pooling, a average pooling, or a sum pooling? I can also, these two parameters tell you the stride, how fast you should sweep this filter or window across the image, and also padding. You can add padding to the input image. So there's all these different types of features you can have. So of course, because a CNN involves fully connected layers, we can actually also implement the exact same neural network shown in our demo using the convolutional neural network structure. It should look like this, just having 3 full layers. And with implementing CNN, we have kind of a shortcut to do all the SGD training for you in one step, connected to the convolutional neural network class. Basically, you just call conv.trainsgd, pass your data set, your learning rate, your squared laws, etc. And yeah, it handles all the SGD for you. So basically, these 2 lines are all you really need to actually train a full model. You specify your model, have this line of code, and then the user can create any neural network they want and train it. So yeah, just to quickly mention some evaluation results. So we did some unit testing, of course, for each of these CNN and NNN to verify that each individual function was doing what it's supposed to. But we also did an integrated test by getting MNIST data, the MNIST handwritten digits data, and we actually constructed these relatively simple networks and said, okay, how well does it actually classify the network? We saw in the demo that it got about 90% accuracy. So we can see that here. Even after just 50 epochs, it still achieves about 90% accuracy, the full neural network. And we see the CNN actually also achieves a very, very similar accuracy after 50 epochs. But notably, the CNN only uses 1,000 parameters, whereas the full NN uses 13,000 parameters, which kind of shows the advantage of the CNN in classifying these handwritten digits. So yeah, but this definitely shows that our neural networks are working. They are able to classify stuff. Yeah, so this shows us a good integrated test of our library. All right.
All right, SVD. So singular value decomposition is a way of identifying axes in which data is very correlated. This often helps in dimensionality reduction. So in this picture here that we got from Wikipedia, it's technically a plot of a bunch of 2-dimensional data points, but if you kind of blur your eyes, it could be seen as roughly 1-dimensional because all the points sort of fall along this line here. SVD is used to identify what exactly this line is. And not only that, but it gives you a basis of the vector space, or it gives you a basis of the plane that the data is often correlated onto, an orthogonal basis, with the first element of that basis being the direction of strongest correlation, and then they're sorted in decreasing order. So mathematically, this consists of taking an n by n matrix and factoring it into 2 orthogonal matrices, sandwiching one diagonal matrix, the diagonal of which is the singular values of A. And we usually sort these in decreasing order. This lets us write A, the matrix, as the linear combination of a bunch of simpler matrices, these UI, VI transpose matrices. Now, each of these has a coefficient of sigma I. Because the sigma I are decreasing, this means that the terms at the end of the sum are not actually contributing as much to the overall product. If sigma 1 is like 100 and sigma n is 0.01, you could probably get rid of the last few terms and not lose too much information. So this is great for lossy compression, for example, with images. So what we did here is we took a couple of different images and separated them into their RGBA channels, and then performed SVD on those channels, and then recomputed it, leaving behind some singular values. So on the top left here, we have this original image of some cute sheep. To the right of it, we have the same image recovered from if we only kept the first 100 singular values of the matrix. On the bottom left, we have the up to the first 50 values, singular values. So this is about 40% the data of the original image, and you can still see it's a little bit grainy, but still recognizable. Once we get down to below 10% compression rates, it becomes just unrecognizable. So same process going on here with this cat named Panini. We can see that the compression rate scales very, very well with the dimension of the matrices. So this is a much, much higher resolution image than before, and we're able to get much, much better compression ratios without losing too much visual information of what's going on here. So even the third image here, only keeping the first 50 singular values, it's 20% compression, but you can still kind of see what's going on. Okay, the last very minor thing that we have in our library is a quick line of best fit program. And this is just because the first singular value, or this first singular vector, when you compute SVD, is the vector that represents the line of best fit if your data is centered at the origin. So we'll do a quick demo here, if I can get to Desmos. So here I have a cluster of data points, and I've went ahead and written them as the columns of this matrix called data. And if I run this, I can compute the vector that spans their line of best fit if they are centered at this point here. So if I go ahead and plot this, I can see that if I compute their mean, sure enough, the mean is in roughly the center of the data. And if I draw the line, okay, if we draw the line that goes through this point and has the slope as indicated by our program, we can see, sure enough, it's basically a line of best fit. So that's just some extra fun functionality that we have. Yeah.
Okay, thank you. Here are some references, and yeah, thank you. We had fun making this project.
Yeah. Have a good one, grader. Happy end of the year.